All right. Hello, everyone. Thank you for joining. Thank you for being part of here. Okay. He got shocked by the door. You saw him flinch? Yeah, he got shocked by the door. That's pretty funny. All right. Hello, everyone. Welcome. Thank you for coming. We're going to be going over a problem that Giri gave yesterday. And it's actually the problem that he gave in his midterm for his algorithm techniques class. So that's pretty cool. And it's called stacking cups.
Wasting my time.
Did the door shock you?
Yes, it did.
It did?
That's why I jumps.
So this is the title of the problem. Now let me give you an explanation of what it is. Let's say you're at a county fair and there's a couple of stalls. So let's say you have n stalls. And at each stall, they give you a certain cup of a certain size. So for C of I, for stall I that's less than or equal to there we go. So each stall, they give you a cup. And let's say that cup has a size of 1 or greater than 1 or less than or equal to, let's just do 1,000. So now let's visualize it a little bit. This is nice to see the numbers, but to make it a little bit easier for us. Say we are given 5 stalls. This is C of 1, this is C of 2, this is C of 3, this is C of 4, this is C of 5. And then each cup has its own number. We can say 1, 7, 4, 2, 9. With this information, our goal is that we want to stack these cups. The way we to stack them is, let's say we can put 7 and then 4, we can put them right on top and they can stack easily. You can think of 7 as the radius of this cup. Therefore, you know 4, that this next cup has a radius of 4. You know it will fit on top of the 7.
It's like the towers of Hanoi.
Sure, the towers of Hanoi, yeah.
Okay.
So that is our problem, and we want to get the certain sequence that has the largest possible cups we can stack. You guys understand it so far?
Wouldn't it just be all of them together?
No. You cannot stack 1 and 7.
You can't stack 1 and 7 on top of it, so there has to be an order in which you stack them.
It's not, the order is also by the order you see it. Let's say I get 1 and 7. You cannot put 7 before and then stack 1 on top of it.
So when we say stack, like what do we mean by that?
Yeah.
I don't understand. Like how would the output for this input be?
So for here, for example, the answer would be 3. Because we can stack 7, 4, and 2.
Oh, so you're returning an integer value, not the
Yeah, no, you're not returning which cups you're stacking. You're just returning the maximum number of cups you can stack.
Okay.
You cannot do 1 and 7 because first you obtain that cup 1, and then when you saw 7, 7 does not fit in 1.
Okay, so we're trying to find the longest consecutive descending numbers. Hold on.
Yes, you're onto something very big there. If you can tell me, let me repeat it for the live stream. He said that we're looking for the longest, not consecutive, the longest sequence of decreasing numbers. Is there another problem?
Monotonically decreasing subset where when you add them up together, it's the largest.
Listen, you just said so many words.
Okay.
Try to shorten that down.
Decreasing, add them up, largest amount.
Yes, but there's another problem that's similar to this that I want you guys to get at. I didn't actually think you guys would jump at this quickly, but it's good that you did. So Joseph, you said it. You said the main thing. You're looking for the longest sequence of decreasing numbers.
Okay.
Is there a problem?
The technique?
Is there a problem similar to this?
Well, I don't know the problem name, but I know the technique. You
I know
want me to
what-
tell you the technique?
What?
I did it on
Sliding
Leak.
window?
No.
I did it on Leak. It's the self-stock. No.
Okay. The problem is the longest decreasing sequence.
Oh.
LDS. You might be more familiar with longest increasing sequence.
You mean subsequence?
Subsequence, yes, sorry, subsequence.
I use that for the buying and selling stocks, I think.
So let's say it's another very common problem. We can have like 1, 2, 4, 3, 5, and then 8. Longest increasing subsequence could be 1, 2, 3, and 5. Yeah, 1, 2, 3, and 5. Do you see that?
Oh, so wait, hold on.
So you can jump in between, so like.
Exactly. Does not have to be contiguous. You could jump. And that's exactly what could be here as well.
It could be a -1 after a 9.
Sorry?
Like a -1 cup.
No, there's no negative numbers. I said this is the constraint. But yeah, this is just another problem that is extremely similar to this one. Longest decrease in subsequence. And we're going to solve it pretty similar way with dynamic programming. Why is it dynamic programming? Why is this not greedy?
There are optimal sub-solutions.
There are optimal sub-solutions.
Like, it has sub-problems.
It does have
There's an
sub-problems.
optimized solution for each.
Yes, I do agree with that. And also we need to take into account the future values. For greedy, once we're up to here, we know everything before, but we're not taking into account what we might see in the future. For dynamic programming, it does. Is there anything you want to ask me to like catch you up?
I mean, I don't know. I've never seen anything like this. So you can keep going.
Okay, just let me know if anything.
But I think I understand. So you can jump. So I guess like what you want to find like the largest. I mean, no, it doesn't even matter. You find the largest number. You just want to find like. I don't even know how you would approach it.
It's like the longest decrease.
Yeah,
And it starts with 7.
yeah, but like how would you like code it? I don't know.
I'm actually going to be showing the code.
We're gonna get to that.
Because there could be like a number in between that's bigger, and then you just kind of like forget it. Like I mean, you don't forget it, but you skip over it.
Yeah, it's like a.
What's the answer for this?
It'd be 5.
Why?
You start at 7, and
Yeah.
then you skip over 9, and end at 1.
Yeah, 7, 5, 3,
2,
2, and 1.
Yeah.
So let's continue. I know you guys are talking about the code, but let's continue. For right now, do you guys understand this problem?
Would this be a 1D or a 2D?
1D.
Yeah, it looks like 1D.
Could be actually.
No, maybe it is 1D.
It is 1D. It is 1D. Yes. Good. Okay. So, perfect. I'm going to erase these constraints. I'm expecting you guys already remember them. So this problem is relatively easy compared to the other problems Gary has given us, as you can probably tell. Okay. So we all agree this is dynamic programming. You're not completely sold on it?
Honestly, I have very little experience with dynamic programming.
Okay.
It's not like I can't code up a solution that has
Yeah.
to be dynamic
Yeah.
programming.
Okay. So for now, you just understand that it's not greedy, because greedily choosing whether or not we want to add a cup, it might screw us over later on, because a greedy algorithm does not consider the future options we might be given. Dynamic programming, it changes that. It solves these sub-problems, and then once we get into the future, it determines whether or not we should take this cup by looking at smaller sub-problems. That was probably really confusing. But
Yeah, because you want to get the solution of the sub-problem that adds
Yeah.
on to the bigger one. The overarching, situation.
dynamic programming takes into account all these multiple sub-problems, and at a current position, you get to choose like which of those sub-problems would fit best for that current one. Greedy, you only have like one solution,
Sometimes,
whether yes or no.
Sometimes it involves
I believe.
a min or a max.
Yeah, yeah. And as you see, will be a max here. Okay, perfect. So let's go over how to do this recursively. What do you guys believe will be while I draw my boundaries? Do you guys have any ideas so far? That's good enough.
So I guess, okay, so if it's recursively, you need the base case. So I guess the base case is when we're all the way at the beginning and it's a size 1. That's already the answer for that one?
Yeah, sure. Yeah. So you know you're going to start off with 1 cup.
Yeah.
So if you're here,
Yeah, so that's the base case.
you want to use return 1. Because you know there's nothing else that you want to consider.
Right.
So we're going to start our recursive function by looking at the last one in our list. And this last one, let's already consider that this is part of our solution. So far, we have a maximum of 1 stackable cup. Now, for here, how do we consider how many other cups we have?
So if they're larger than the previous cup,
Yes.
the cup you're on.
Very good point.
So we can have like a counter, a global counter saying what's the largest subsequence?
No.
No?
So like he said, we want to look at these previous cups, right, before this one. We only want to add to it. For now, I'm saying add, but I will change this later. We want to add to it if it's, in this case, greater than this one, correct? That's the only way we can stack it. You guys agree with that? You said it, so.
Yeah.
Okay, cool. How about you, David?
Yeah.
Do you agree if we're currently looking at this cup?
Yeah.
We want to look at all the cups before it and add to the amount of total stackable cups if they're larger than 1.
Okay, so wait, could we all just initialize it all to 1 just to start? Like before we even recursively count?
It's a little bit more complex than that.
Really?
Yes.
Okay. I mean, we'll go along.
Yes, but for so far, do you understand this?
Yeah.
Okay, cool. Now, something else you're missing there. So let's say we want to take the maximum, right? We want to look at the ones before it. How do we do that so far? We know this current position. How do we look from the beginning up to right before that position? We use a for loop. We use a for loop to look at from the first one up to right before the current one we're on. Agreed, right? Simple so far. Perfect. Let's say this 2 is larger than the 1. We might want to include it, correct?
Yeah.
Perfect. Cool. Now what? Do we just want to increment by 1? No. Why?
Wait, what do you mean increment by 1?
Like here we have a
Set up a table.
crap, sorry. Let me use the right answer. Here, when we're looking at this one, we know we have a maximum so far of 1 stackable cup. That's the best we can do so far because we're considering it. We can take it. Why not? At this 2, do we just increment by 1?
You found a bigger one than the one at the end? Technically, yeah. I mean,
Technically, yeah, okay.
It's gonna be 2, not 1 anymore.
Okay. What do you think? Is there something else that we want to do? You don't know?
Then
Okay.
again, like, it
W-
could also be
So what we want to do is not only take into account once we see a larger number, we want to take 2, right? But we also want to take the cups that are larger than 2. So if we're doing this in recursive function,
Oh, yeah.
you see how it makes sense?
Yeah.
Okay, cool.
Like, we were gonna go to another index in the array that was like
No.
arbitrary. But yeah, you would go from 1 to 2, and then you find any number that's greater than 2, and you find any number that's greater than 4.
Exactly. So that's part of a recursive function.
Yeah.
Perfect. So you saw it. Nice. Thought that was gonna be difficult to see. Have you seen it so far? You can say no. It's fine. No. Okay. Perfect. So we start off with 1, right? But now we're looking at 2. 2 is greater than 1, so we might want to consider adding it to our stack.
Yeah.
So what we do here is answer is equal to max between answer and, what do you want to call this recursive function? Solve?
Yeah, sure. Solve. And then change the solve to. Okay, so because we're.
Because we're looking at this.
Okay. Wait, hold on. Are we looking at this as a range or?
Sorry, it shouldn't be solve 2. It should be solve 6, because that's the index value.
Okay.
Yeah, there we go. Because we want to take into account this 2 plus all the cups that are greater than 2. And we can do that easily by just calling this recursive function.
Yeah.
It will be the exact same thing now at 9. Let's say we took 2 and answer got updated. Instead of 1, we got a better answer of, let's just not actually try to do it right now.
Actually, what about for 7?
What? What?
Wait, actually.
Like, can you close the gap in between the 9? That was a 4.
Yeah.
The arrow is for the 2. Right, not the 1.
Yeah, this blue arrow is for the 2. You're saying, how about the 7? When do we include the 7?
I mean C7. Like, what do we say? Ans max and solve 7 plus 1.
No. We called initially. We
So
just
we're
did
in the
solve 7.
We're in C7.
Yes.
And then that's
We started at C7. That's where we initially
Okay,
began the
okay.
recursive function.
Okay. I was getting confused between where that was being called.
Yeah. So now this 2, I'll do it legitly. It's going to call solve 6, which is now here, right? Now it's going to call solve 9, whatever. But 2 is going to return 1, 2, and 3. So 3 plus 1, 4. 1, 2, 3, 4, 5. Sorry. Plus equals. No, it's just going to be max, actually. Not plus equals, my bad. 6, 1, 2, 3, 4, plus 1, 5. 5. Does that part make sense? Because solve 6, when we call, now we're looking at 2, and we want to do everything before, right? I'm skipping a couple steps. I'm just looking at it. I know if I call my recursive function on 2, it's going to return 7, 5, 3, and 2, which is a size 4. And now since I'm at 1, I'm doing that 4 plus 1 to include 1, and I get 5. When we call this, now instead of looking at 2, we're looking at 9. Our answer here is 5. And if we call solve 9, let's see. So solve 9, now we're in a recursive function. I want you guys to first visualize it. I'll write it out later, I swear. Solve 9, the best we can do is 1 cup. 9, right? Now we go before. Is there anything greater than 9? Nothing. So we just return 1. So solve 9 is going to return 1 plus 1 is going to be 2. And of course, that's how we decide that we don't want to take 9. It will give us a worse solution. It was better to take 2 and stay with 5.
Okay, so we don't include 9.
Exactly. And now we skip from 9, we go to 3 because we're doing this for loop.
Before this, we had to do a for loop and count how many were bigger before. Say 2.
Yeah, so here.
But wait, but if there's none bigger than 9, wouldn't it actually be 0?
No, because we need to take 9 itself, which is 1.
1. Okay.
Yes. So now let's create this recursive function. No. Let's call it position, or POS. What's the first thing we mentioned? Initially, we want to start off with 1 because we will take this cup. We want to include it in our answer. And now, like you guys all agreed on, we want to do a for loop from the beginning right up before that position.
I mean, if the answer is 1, then why are you adding 1?
Huh?
You would have to start at 0, wouldn't you? 'Cause, I mean,
No, because you're doing the max between answer, which is answer is 1, or whatever this solve is. So solve for 2 plus 1, including this one. In range of 0 to position minus 1. Don't call me out for the Python code. I know this is wrong because it's already exclusive, but look at this as pseudocode. For this, if the cup at position I is greater than the cup at position POS, which is the current one we're on, if that's the case, that's when we want to update our answer.
And equals max and then solve I plus 1. Oh, that's the DP part.
This is the, this is the DP part, yes.
Yeah.
And then of course we just return our answer.
So it's just a vanilla recursive solution. This is not memoized yet.
Yeah, this is not memoized at all yet.
Okay. Oh, well, we need a base case, no? Don't we need a base
We don't really need a base case.
So then when do you stop calling?
Oh, well,
When do you stop calling solve? When does solve stop calling itself?
at 1, 0 to 1 minus 1, 0. This for loop would not run. It would not call solve.
Right. Yeah, right.
And then you use return 1.
Okay, yeah, right. Wait, so shouldn't we 0 index those cups?
No, because here 1 minus 1, 0, 0 and 0, it's fine. It doesn't really matter. It works out because I did minus 1.
Okay. Yeah, that's fine.
Do you see how this works? Or do you have any questions on it?
when you call the function, what do you put in solve? 0?
Huh?
When you call the function for the first time, what do
You call in the last one.
Yeah. Recursive is.
Oh, so you call the function and you put in the last one.
So let's say
Okay, yeah.
this is all out of this now.
Yeah, like your main, you would call the last index.
Exactly. Solve, in this case, let's just call it length cups. Sorry. If I'm doing C up here, I might as well do C.
Length cups minus 1. Or, yeah, length cups minus 1.
So I'm staying with pseudocode. I don't want them to think it's actual Python, but
I mean, I can read Python. Yeah.
Okay, so
I'm
can
gonna
you
better
take
at
out the
reading
minus
Python.
1? And
You can
then
do length cup.
Yeah.
Practicing my Python.
you've been practicing with
I love
Python, good.
that. I love that.
It's pretty simple.
Mm-hmm.
There we go.
Oh wait, don't we need to pass in the array of cups?
No, a global variable.
Okay.
You guys see how this works?
Yeah. Because then
Pretty easy, right?
you're just gonna get the max up to there. add
Yeah.
that.
Do we need memoization?
Oh yes, we do.
Why?
Because if you're going to, so for 1, you're going to call for each, but then for each, you're also gonna call for everyone else.
Give me an example.
It's gonna be, so like,
And squared.
no, it would not be n squared.
It would be n squared.
It would be n squared?
Yes.
Hold on, 1 calls 2.
We have
but
2
one
for
also-
loops.
What is it?
This method itself is going to run through the whole array. And this for loop inside the method also runs, worst case, the whole array. So it's n squared.
hold on a minute. That's the thing though. You're calling one, right? And then one's gonna call this one, right? But then that
Here,
one's
write it
gonna
out.
call it. Okay, look. So I'm saying. So so we're gonna go C7. Goes through C1, right?
Yeah, it goes through all of them up to
It goes
C6.
To C2, C3, to C6. But then this one also calls up to C1 as well, which is why we're doing the DP part, right?
Mm-hmm.
And then this one goes C2, which we also called before. Oh, and hold on, made a mistake. That should be C1 and C2. And then calls C1 and C2, and this is a 6, calls C1, C2, C5, and then C1, and then so on. So this is actually an exponential
Yes.
recursive function, not, I mean, it's not really n squared.
It is n squared. No, it
The
is.
for loop.
Yeah.
Okay, but the whole recursive tree isn't.
Yeah. But it is. I'm pretty sure because he even included memoization himself, and it is n squared.
Oh no, with memo?
Yes.
Oh yeah, with memo it's
Okay.
Okay. Oh, or I'm not on the same page.
No.
Without memo, this.
Oh, I see what you were saying now.
Without
Oh,
memo,
okay.
Without memo, it's like that.
Yes, without memoization, it is not n squared. It's something way worse.
Yeah, we're not memoing.
Okay. I thought. Yeah, we were on the
We're
wrong
not the same
page.
okay.
All right. Can they see this?
It happens.
No. Okay. Cool. All right. So David explained it beautifully. We do need memoization. Because we're going to run through this whole list. And then once we get to 3, we're going to call solve on 3. Then 3 is also going to run through the whole list. And as you can see, there's an overlap between these first 3 cups.
You have to
And that's unnecessary.
You have to recalculate values.
Exactly. So, where will we add memoization?
Create an array of Boolean, right? If you've seen it or not.
Mm-hmm.
That's
A Boolean, an array of Boolean, no.
like visited.
Well, you have the value.
That array is with the length of cups, and that index represents that cup's answer. So, instead of now just returning answer, we do memo.
Oh, I've seen a question like this.
Yeah?
I know what you're saying now. I've seen a question like this
Return
on a
memo.
2D matrix. I don't know if you know what I'm talking about. Have you seen that? Yeah, and it's like finding the longest sequence in a 2D matrix.
Or it is increased.
You ever seen that one? Yeah, it's increasing, and you find the
Oh
longest.
yeah.
The what? Sorry, say it again?
Finding the longest sequence in a 2D matrix. Have you ever seen that question?
Wait, is it like?
And they have to, the path has to
Oh,
be-
I have seen it. Yes. You get this certain position, and then from here all the way to the longest it could go.
Yeah.
Yeah, it's exactly that. It's exactly the exact same thing.
Yeah.
Yeah, that's you still want to use the memo table for something similar.
To reduce your recursive tree. To prune it. To trim it, exactly.
Okay, cool.
You trim.
Harvest it.
Harvest.
Harvest it.
Yeah. Okay. So this is the code. Does it make sense? Is this right? I think that's right. Is it unnecessarily called this way? It's going to. No, it's not right.
Yeah. Well, you need to add something up there.
Real fast array.
No, global variable.
Memo is gonna be global. Memo pause. Or that. Oh, it's gonna be a dictionary.
Sure.
Memo pause. Actually, could you indent it instead? I think it's more.
Yeah, sure. Beautiful. Now it works. Now it's right. Sense? Makes sense?
Yeah. If if it's already calculated, don't even go through
Exactly.
recursive
Yes.
for loop, just return what you calculated.
Yep, so here's your base case.
Yeah.
Comes into the memoization part.
Yeah, for mem.
Yeah, from mem. So if it's already, we already done this calculation before, you just straight up return it. If we haven't, do that calculation, store it in your memo, then return it.
Yeah. Makes
Beautiful.
perfect sense.
What is the time complexity of this?
Yeah, it seems n squared.
Yes, n squared.
Since 3, okay, say we're in C4, well, all the other values were already calculated before.
Yeah.
So it's just gonna add on to it.
Mm-hmm.
It's just gonna do a max at a.
But it's still going over the for loop.
Yeah.
This is just going to be returned a little bit quicker.
Mhm.
It's like n squared over 2, but then like that it totals up to n
Well,
squared.
it's n squared. No, it's n times n minus 1 divided
Mm.
2, or n plus 1.
Plus 1. You're doing the formula?
Yeah. The
Summation formula?
Sigma n. You remember that from calculus?
Let's not go there, man.
Alright, fine.
Okay, it's fine, it's fine. But this is the big old notation. Is this the best we can do?
Uh,
We can do better.
can we do that?
Can we do better?
Oh, man, I feel like I'm in an interview.
I'm gonna die.
It's like, damn.
How can we do better, guys?
What if, nah, 2D table? Would that actually?
2D table? No.
That has nothing to do with.
You're saying like move it out of the recursive?
Like, do we need a for loop?
Bro, we can put it in a tree.
Like,
What is?
What if we want the
That was
other-
actually my question.
Really?
A balanced binary search tree, but it still doesn't work. That was my answer to him yesterday.
What
Where
if-
is our weakness here? What is making this n squared?
No, it's the for loop.
It's the for loop, okay.
What if we didn't need a for loop?
So this is the weakness.
The point of failure.
POF.
Oh.
What can we do to make this a little bit better?
What if we started instead of going from here, we start from there? We can?
No, we can start here. We can just iteratively start here. Doesn't change the fact that we are getting rid of this for loop. We still would need this for loop.
Oh, really?
Yes. What you guys are thinking of this, I'm gonna write it out iteratively. But you guys are bouncing idea around. Yes, because you guys saw it recursively. Oof, why did I do that actually? Ah, it's fine.
But we can do it iteratively.
We could do it iteratively. It's the exact same thing. But now you do start from the beginning. For the iteratively, it's still n squared, so it doesn't really solve anything. But yeah, we do start from the beginning. Go from here to the front. And that for loop that I had in the recursive solution, you're also going to have an iterative solution.
But I have a question. So wait, so there's no solution better than n squared?
There is.
Oh,
There's an n log n solution.
Oh, log it.
you can sort it.
No.
No.
If you sort it, you lose track of this
Yeah, you're right.
sequence.
Yeah, that's dumb.
This is the whole Google interview.
I'm just thinking sliding window. Like
No, it's not sliding window.
What's the other thing?
D is another array that we're going to be using to solve this. So what if, as we're going through this, we keep track of the best so far?
what if we sort it, but then we
No.
keep track of the index?
No.
Then when we're looking at it, it's like.
No, wait, but then we lose the ordering of 5, 3, 2, 1.
Okay, so here's the answer, guys. As we're going through this, we also want to keep track of the largest we've seen so far. And then once we are looking at a new cup, we do binary search to see where that new cup lands and see what is the length from the position it landed and all the larger cups to its left.
Wait, what?
Yeah, I know. Let me write it out. First off, let's insert an extra cup called infinity. This is just going to help us out later on. Let's say we have this second array, which will keep track of the largest we've seen so far. Starting off, of course, we will have infinity. And now we're looking at cup 1, correct? The first cup. This first cup we're going to call it F. This will keep track of the numbers of maximum possible cup stacks up to that position. So here we would have 0. Because we're not including that one, so we're just going to set that one as 0. Here, infinity. And now we're looking at 1. So far, if we were to do binary search on this F array, 1 will land all the way to the right. We can't have duplicate values, so let me just change this. There we go.
Can you flip the 2 on the 4?
What?
Flip it, and it's going to be a different result.
Oh, yeah, it's fine. So at this 1, we could take it. In this F array, the 1 is all the way towards the end. It doesn't land between any 2 values. At this 1 position, if we were to do binary search on this F array, it does not land between any values. So we can just add it. And now we have 1 down here. Stick with me. It might make sense later on. At this 7, 7 is between infinity and 1, correct?
Yeah.
If we do binary search, we know we land right here. So now we replace this 1 and put 7. And this has a value of 1.
Wait. So can D&F be considered stacks, maybe? Okay.
No, not stacks.
So we're just overriding this.
We're just overriding, yes.
Okay, then. All right.
So now let's continue going. At this third cup, we have a value of 5, correct? 5 lands between infinity and 7.
So no.
So no what?
It would be the first.
We replace 7 with 5. Wait, actually, no, you don't.
No, right? Wait, no. So 5 isn't enough. 1.
Yeah, sorry. We don't replace 7. We add it to the end. Because it does not land between infinity and 7. We add it to the end, and therefore we increment that last one we have, which was 7. That had a value of 1, so 1 plus 1, now we have 2. Now we look at 3. 3 does not land between 7 and 5. It lands after 5. So let's go ahead and add it to this F array. This looks at 5, and then increment by 1. Now we have 3 here. 9 lands between infinity and 7, correct?
Yeah.
So now we could replace 7 with 9, because 9 is a larger cup size. And what we do is, right? Wait, give me a sec. Yeah, so everything to the left, 9 would have landed somewhere here, right?
Yeah.
So we want to look at the infinity. Infinity has 0, 0 plus 1, 1. It's the exact same thing we were doing here. For 3, 3 landed outside, so we looked at 5. 5 had a value of 2, 2 plus 1, 3. It's no different for this case. Now let's look at 2. 2 lands between 5 and 3, correct? No, sorry, it lands at the end.
Yeah.
So we can just add it. Look at 3 right here. What value does it have? 3. 3 plus 1, 4. Now let's do 4. 4 lands between 5 and 3. Replace 3 with 4. Look at 5. 2. Increment by 1. 3. So by keeping track of these largest we've seen so far and doing binary search to see where our current cup that we're looking at lands in, we know the length. And as you can see, the length of this F array is also the answer. 4.
Well,
You're lost. Yeah, this is actually pretty hard to explain, I'm not gonna lie.
I just don't understand the binary
do we need
search.
an infinity?
Yeah, we do.
Oh, we do need it. Okay.
Hmm?
I just don't understand how the binary search is being implemented.
So this F array is keeping track of the largest, our best answer so far, right? Because initially we took 1, and then instead we want to take 7.
Okay, so F is an array
Yes. Why did we take 7?
because it's bigger.
Exactly. Since it's bigger, we might be able to fit more cups. So that's why we replace 1 with 7.
So on the first index, so it's a 0. So 0 index is max.
Yeah, this is
The
infinity.
maximum integer
Yeah.
value.
Wait, D and F are both tables. They're both arrays.
Yes,
right?
let him finish. Yeah.
They're both DNF for both arrays?
Yes.
Okay. And you're supposed to create these 2 arrays.
Yes.
Okay.
Okay, that's it?
And then, no.
Oh, okay.
I'm just trying to wrap my head around this. So then the 0 index is max integer value, and then 1 index is you always put the largest number in that. You always put the largest number in the array at any given time in the first index.
For F?
For F.
Yes, if you see a larger number, you do binary search. You know between what numbers it lands.
Wait, well, what do you mean binary search?
Okay, so
Oh, because you're gonna do binary search on that little array down there. So that's an array you build it. Wait, are zeros allowed in the? For
yeah,
cups?
so do. Wait, say that again.
Are zeros allowed as cup values?
I'm not sure.
No, it was 1.
No, yeah, it was 1. It was 1.
It was 1.
So here when we were looking at 4, we want to know where 4 lands. 4 lands where? We do binary search. We're looking here. We look at the middle, 5. So now we do binary search again. Then we know we're going to land here.
Yeah.
Between the 5 and 3, correct? Here, we're going to want to look at the next largest number, so which is 5. So the number to the left.
Yeah.
We see what value that has. It has a value of 2.
Yeah.
We want to increment it by 1. Why? Because this 5 is larger than the 4, so this 5 can include the 4.
Yeah.
It's the exact same thing as when we do recursively. It's the 4.
Oh.
It's the 4 plus everything that the 5 has gotten so far,
That makes sense.
which is why we look at the value.
Wait, hold on. Is this, so this is gonna be a table, it's gonna be a dictionary where the key values are those values?
What?
The
It's
key,
it's a dictionary? It's a hash.
You're really confusing him.
like D is the values are, the numbers we calculated, and then the keys are the values in the upper array.
You can do this as an array with a pair, a tuple, or 2D array where this gives you the number.
I'm just
and
saying that
the-
because in the F, you're gonna have the
Yeah, you need to look at that index, yes.
So, but you're not gonna know, maybe you need to store it somewhere.
You can also use doing F. You can have like a second array and update the indexes as well.
We don't even, it seems like if we just, all we want is the length, we don't even really need the, well, we do need the D, no.
We need both of these.
We need both.
Yes.
Just return the length of F,
Yeah.
and that's the answer.
Or you can look through D and return the largest number. Okay, so going back to what your concern. We know the 4 lands here, right, between the 5 and 3. So we want to look at 5, see what answer that has, see how many cups 5 can hold, and then add 1, because now we're going to be adding 4. So that's how we get 3. And then we update 3 to be 4, because 4 is larger.
And then what do you return?
The length of F, or we look through D and return the largest number we find.
Yeah.
Isn't D a hash map? Or
No, ignore what he said, no.
Yeah, I like to look into D.
Yeah, you can do that too, then.
You could do that.
So it's 2 for loops.
It's 1 for loop, yes, and then a binary search, so while loop, for loop, it's going to be while loop. If you do it with a for loop, I don't know how, but yeah.
Yeah, that's a while loop. And then then, okay, so it's a for loop, and then a while loop inside, making a binary search.
Which is
And
log.
you could also have an integer. You can have an integer keeping track of the longest of the highest one.
Yeah, you can do that too.
Do that extra for loop.
You can do that too.
Interesting, yeah. And so every time you go into the for loop, you do a log, binary search.
Yep.
Log linear.
I think you could do it with a for loop instead of a while loop. This is something extra. If beforehand you compute the log number of the array, you would do binary search on, and then for loop starting at 0 up to that log number.
No, man.
No, of course, but I'm just saying, like, that might work, right? Okay, never mind, ignore it.
Like this is simpler. This is a lot.
No, this is for sure simpler. I was just. So, okay, what's our time complexity now?
And log n. Oh, you write the O in the middle.
Yeah, I don't do n.
LG.
Do you say n, ln, n? No, you say n log
It's
n.
implied. It's a silent. It's an implied O.
It's a silent O. Okay, so pretty much it.
Yeah, interesting.
Good problem, Lazaro. Thank you.
Thank you guys. All right, so hopefully you guys enjoyed. If you want to look more into the problem, I highly recommend looking at Giri's lecture, which is also on a YouTube channel. He went really in depth. He even has some nice slides. But this is just some more discussion for the problem. Sometimes it just helps. I also want to mention, guys, if you're watching our live stream, make sure to come to the second general body meeting of DSC FIU. It's going to be in PG 6 116 at 5. We'll be there today. We'll be there. If you can't make it, we're also going to live stream it, so no worries. But other than that, thank you guys.